Welcome to Learning to Engineer. In this video, we will be seeing how to reduce a network. The first step in this process is that we need to find out which set of resistors are in series in the network and which set of resistors form a parallel network. For that, we should be able to correctly see the circuit with the perspective of the source. I will tell you how to do that. Next, we need to check if there is any while loops and delta loops. Regarding this, I will be doing a separate video on this topic and link it in one of the cards here. Let's get started. You are seeing two circuits here. Most of you might have known this is a series circuit and this is a parallel circuit. In a series circuit, the current enters to one of the terminals. It is passing through the resistors one behind the other. That is, once the current ejects from the first resistor, it will be entering into the second resistor and then returning back to the source. This is a series network. Most of you might have known this. And this is a parallel network because when current enters, it splits into both the resistors, goes through them, and then it is coming out of the loop back to the source. This is a parallel network. For more information on the voltage division and the current division concepts in series and parallel network, click the link here. Whenever we say that two resistors are connected in parallel, we mean that they are two different devices, maybe an electric iron or a bulb, a thermostat, anything. We represent any load that uses the power that you are sending as a resistance. This resistance can actually be anything. You can imagine that the wiring in your house is similar to this network, wherein you will have a power source, say like this. This will be a AC source, 50 Hz AC to 30 or maybe to 40 volt AC, and this power source will be sent across different transmission layers or different transformers. This power source will be sent to all the supplies that we are connecting, maybe a plug point which has a electric iron, maybe your fan, maybe a bulb. This is the domestic connection actually. So you can imagine that these resistances are represented in this manner. We will have, we'll say 50 ohm or 60 ohm written across it, which tells that what is the value of this resistance. This resistance can be either 50 ohm or 60 ohm or any kind of a value, and this value is measured in ohm. It can be shown like this also. There may be, this is a bulb, this may be a device which uses current. This is the practical drawing of every resistor. Before we proceed with this circuit, I hope most of you know what a series connection and a parallel connection is. So, pause this video for a moment and try to answer this. Whether X and Y are in series or in parallel. I hope you guys have answered this question. Yeah, keep your answer noted in a place. Let's proceed with this video. Now, what I am doing is, for these X and Y, I am introducing a power source in this manner. Initially, you didn't have a power source. Now, I am putting a battery here. Okay. So, now answer me whether this is a series circuit or a parallel circuit. I hope most of you would have told that this is a series circuit, because the current is entering the resistors one behind the other, like I told, and then it is returning back to the source. So this is a series circuit. Yeah, you are right. Now what I am making is, I am putting a power source like this in this circuit, like this. Okay, so in that case, we all know that this is a parallel circuit. Why? Because since the power source is introduced in this terminals, the power is getting divided among X and Y. So this is a parallel circuit because of the current division that is happening here. In the series circuit that we saw, there is no current division. But in this circuit, the current is getting divided. That is why this is a parallel circuit, and that is why this is a series circuit. So coming back to my first question, which doesn't have this power source, I was asking whether this is a series circuit or a parallel circuit. We cannot conclude the circuit whether it is a series or a parallel without knowing from which terminal the current is going to enter. Or without a power source, we cannot conclude whether this is a series circuit or a parallel circuit, because when there is no power source, we do not know how the current is going to enter. The current has to decide whether it is a series connection or a parallel connection. So think from the perspective of the current that is going to enter these resistors, whether the current is going to have a path like this or a divided path. That will make you answer the question whether they are in series or in parallel. When you do not have a power source, you cannot conclude in which perspective you are going to see. Generally, we see the circuit in the perspective of the current. So, I hope you have enough understanding of series and parallel circuit. If you are still having some doubts or confusion, click the link in the description or here. You will have a good idea about how to reduce a resistor network which has series and parallel networks, and you will also know how the voltage and the current divides. Let's solve this circuit. Find the equivalent resistance of the network shown in the figure. In this figure, we have a loop and there are two shorts in it. We have to find the equivalent resistance from this perspective, meaning that in future I will be having a power source connected between these two terminals. When that is the case, current will be passing through 2 ohm, then it will split across two loops, then combine back, then go here. So this is the nature of the circuit. Whenever we see a circuit, we must first try to reduce it in order to find the objective. Here our objective is to find the equivalent resistance. So we need to first reduce this network without affecting the nature of the circuit. Meaning that these two resistors are in parallel according to this circuit. Even when we reduce, we should not change the nature of this circuit. So in order that I have to reduce, what is the first thing? I am imagining that current is entering into 2 ohm, then splitting across 15 plus 10 and then these two resistors. So basically these two terminals have the same potential and these two terminals have the same potential. So the first step, I am just going to make this short into one single node. 2 ohm resistor, then the circle node which has, I am just putting it as 15 plus 10 as one single resistor. This is 15 plus 10 ohm. Then the same thing has 40 plus 10 connected in series. Also, we have one more resistor 20 plus 30 going from this circle node to the triangle node. Similarly, 40 plus 10 is also going from circle node to triangle node. We have to understand that these two are single points and these two also is a single point. So, from circle to triangle, how many resistor paths we have? 1, 2, 3 paths. Therefore, all these 3 sets of series resistors are going from the circle node to the triangle node. 15 plus 10, 40 plus 10, 20 plus 30. This is 20 plus 30. All these 3 go from the circle to the triangle, circle to the triangle, circle to the triangle. Then in the triangle node we have one 8 ohm resistor here, right? Then this is circulating back to the source. Both these networks are same. Just to verify, what I will do, I am imagining that I am passing a current. So a current is going into the 2 ohm to the circle node. Current is going from 2 ohm to the circle node. Then in the circle node, I have 3 paths. 1 path, 2 path, 3 path. First path, second path, third path. All these 3 paths are terminating into the triangle node. This path is also terminating in the triangle node. This path is also terminating in the triangle node. Then this path is also terminating in the triangle node. Yes, this is also terminating in the triangle node. Then this path is also terminating in the triangle node. So 20 plus 30 is also terminating in the triangle node. Then my current goes from this 8 ohm resistor back to the source. 8 ohm resistor back to the source. So this is also right. This is how we need to verify whether the reduced network is an exact equivalent of the given network. Sometimes when we have short circuits in our circuit, it is easier to get confused and make mistakes while reducing. This will be very costly when we are trying to find the equivalent resistance of a network. Now if I have to reduce this is going to be a child's play now. So the equivalent resistance will be 2 plus 15 plus 10 is 25. 25 parallel with 50 parallel with 50 plus 8 ohm. I have told you a small trick. When two equal resistors are in parallel, the effective resistance of this combination will be half of the resistance. Click the link which is here and then you will be able to understand this concept better. So when I reduce both these, I will get 25 ohm. So 25 parallel with 25 plus 8. So this equivalent resistance is 2 plus 12.5. Again, two equal resistance connected in parallel amounts to half of the resistance. So the equivalent resistance of this will be 12.5 plus 8, which is 22.5 ohm. Okay, this is the equivalent resistance of this combination of resistors. I am going to give you a task. I will test you whether you really understood the concept of reducing a network correctly. Okay. Okay. The first thing that you are going to do is you are going to pause the video after I give you the task. Then you are going to solve it by yourself. Then come back to the video and continue watching the video. Yeah. So here goes your task. Okay. I have replaced this circuit with a short and then I am opening this short and this is the terminals across which we need to find the equivalent resistance. Meaning that in future I will be giving my power source here and the current will be sent via this terminal. It will be sent here, it will go round, then it will come back from this terminal. So this is how we need to find the equivalent resistance. The first step is, like we did in the previous case, I will just mark the circle and the triangle nodes. I am putting this as circle 1 and this is circle 2 because they are different terminals. Okay, this is my triangle terminal, this is my triangle terminal. Okay, if you are still here continuing to watch the video without trying it by yourself, I will highly recommend use this method. Put circle 1, circle 2, then the triangles, then try to analyze the path of current where the resistors run from circle 1 to the triangle, circle 2 to the triangle. Then it will be a very easier circuit from which you can find the equivalent resistance. So I really expect you to pause the video at this stage at least, then continue solving the problem. Okay, I am going to solve it for you. What's our first step? We must reduce this network. We have a circle 1 here. From this circle 1, we need to... Hey, before I continue, I just want to say you something. I have added chapters in this video and in case if you have solved the problem by your own self and if you don't feel like continuing to watch the video, you can use the chapters bar of the timeline and then go to that specific location where I have the answers for it. You don't have to watch the entire video and waste your time basically. Yeah, continuing with the solution. This is my circle 1 terminal and from circle 1 terminal I have two paths of resistors. Okay, one path is from 2 to 8. The second path is from circle 1 to this triangle which is 15 plus 10. This is 2 plus 8 ohm. Since it is series, I am just adding it like this. Okay, this is my triangle terminal. This triangle is same as this triangle. Okay, but this circle 1 is not same as this circle 2. That is the point here. From circle 1 to triangle, we have another path, 15 plus 10. Okay, we have a terminal called circle 2, from which another two resistors are traveling. Between the triangle and the circle 2, we have two paths, 20 plus 30, and then from this triangle we have 40 plus 10. Okay, 20 plus 30 is going from this triangle to circle 2. 10 plus 40 is going from this triangle to circle 2. Basically this triangle and this triangle are same. I'm sorry. This node and this node are same. That is why I am denoting it with a triangle. It means that whatever potential is here in this node, same potential will be there in this node as well. 40 plus 10 ohm, then 20 plus 30. We need to find the equivalent resistance from this path. Okay, it is very easy now. So the equivalent resistance is 10 parallel with 30. Oh sorry, 15 plus 25 is 20. 15 plus 10 is 25. It's not 20. It's not 30, it is 25. Sorry, 10 parallel with 25 plus 50 parallel with 30. If you solve this, you are going to get the equivalent resistance, which is 25 into 10 to 50 divided by 35 plus, oh this is not plus, this is parallel. 15 to 30 is 5 3s are 15, 00 divided by 80. So this resistance is going to be 250 divided by 35. It is 7.142 plus 1500 divided by 80. 18.75. 25.892 is my resistance. You guys have to correct me in case I have gone wrong. Okay. And let me know your solution. Just take a photo of it and post it in the comment section, or you can mail it to learningtoengineer@gmail.com. I'll be happy to see your solutions. Okay, so I hope there are still some people who are watching this video without even trying out the problem even when I paused for the second time. So here is a task for you guys. What you are going to do? This was our original circuit, right? Now take it as an exercise. I am shorting this and I am opening this short, not this one, the triangle short. Okay, the triangle terminal short I am going to open. You are going to find the R equivalent from this perspective. Take it as a task. I am really not going to solve that. You can just solve it for yourself and let me know your answers. For more information on series and parallel circuit, click this or this link. And let me know your thoughts in the comment section. See you again with another video on Tuesday. Thank you. Thanks for watching this video. Have a great day. Bye.